Okay. All right. Yeah. Welcome back. So one last topic is pending from module 1. Okay. See, module 1 is quite vast. Okay. Once we are done with module 1, the later half of AIC is pretty small, especially module 3, module 4, etc., etc. Okay. So we can pick up the pace when it is needed. All right. So fine. So today I'm going to deal with the last topic, that is transistor switching. Okay, so you see in the previous classes we spoke about the biasing, right? Now in the previous classes more emphasis was given for fixing the Q point at the center of the load line. Okay, so we said that if the Q point drifts from its center location, we called those biasing circuits are bad biasing circuits, etc., etc. Okay, so today let's pay our attention to the switching concept of transistor. All right, now you see the switching transistors are different from the normal transistors. All right, in the sense the switching transistors, okay, will have very small on time and off time. Okay, on the other hand, the normal bipolar junction transistors, which are extensively used for amplification purpose, okay, will have a moderate turn on and turn off time. Okay, so the switching transistors are altogether different kind of transistors. They are available both in bipolar junction category as well as in FET category, that is field effect transistor category. All right, fine. Okay, now to understand the concept of switching transistor, okay, first we need to understand the characteristics. Okay, what exactly the ideal switching characteristics is all about and the practical switching characteristics is all about. All right, now first let us consider, okay, ideal switching characteristics. Okay, what do you mean by a switch? Switch is a device which either gives on state or off state, right? You can take an example of your mechanical switch, which is used to control typical electrical load, say tube light. All right, either it gives on state or it gives off state. Okay, so in case of ideal switching characteristics, it is expected that when the switch is turned on, okay, when the switch is turned on or when the transistor is turned on, the collector current should flow through the transistor, okay, and the collector current ideally should be as high as possible. Okay, so when the transistor is turned on, the transistor gets into saturation region, right? We have already seen in case of saturation region, okay, the current is maximum and voltage is 0 because saturation region analogous to short circuit phenomenon. Okay, so this is your saturation region. Okay, so on condition means saturation region. On the other hand, when the transistor switch is turned off, the device gets into cutoff region, because in cutoff region current is 0. Okay, in the cutoff region current is 0, whereas voltage is maximum. Okay, so this is the ideal switching characteristics. Okay, it takes the shape of, you can say, step, right? On step and off state, that's all, only 2 states. Okay, However, in case of practical switching, you do not get this staircase waveform. Okay, the practical switching characteristics differ, slightly from the ideal characteristics. Okay, so in figure B, okay, I have drawn practical switching characteristics. Okay, is it clear, the figure B, or you want me to zoom in a bit? It is legible, all the letters. Can anyone confirm?
Yes, sir.
Okay, fine. So this is what the practical switching looks like, right? It's a kind of, bell-shaped, flat-topped bell-shaped curve it gives. Okay. So ideally, when you supply a current, a base current, the transistor should get into the saturation region. Okay, instantaneously, right? Instantly, the collector current, okay, should rise to the maximum value over here. You see. So at t equal to 0, okay, first let me talk about the axis. Okay, your y-axis is your time axis, and your y-axis is your current axis, collector current IC, and your x-axis is your time axis T. Okay, so when the turn on is initiated at time t equal to 0, in case of ideal switch, the collector current instantly jumps to IC saturation value. Can you see this? It instantly jumps to IC saturation value. That means to say, ideal switch doesn't exhibit any sort of delay. Okay, so the delay time in case of ideal switch is 0. Okay, on the other hand, if you go to practical switching, okay, the device which are available practically, okay, the moment the switching is initiated, okay, at t equal to 0, you can observe that the collector current IC, okay, collector current IC doesn't rise to IC saturation value instantly. Instead, it takes finite delay time to reach to the saturation current. Okay, so basically the T on, the time interval T on talks about the turn on time of the switch. Okay, a practical switch. Now this turn on time is consisting of two components: the delay time and the rise time. Okay, the delay time TD. Okay, it is defined as the time taken by the collector current to rise from 0 to 10% of the IC saturation value. Okay, so TD is nothing but time taken by the collector current to rise from 0 to 10%. So 10% is 0.1 IC saturation. Okay, so that's your delay time. On the other hand, rise time of the switch is defined as time taken by the collector current to rise from 10% to 90% of the IC saturation value. Okay, so time interval measured from 10% of IC saturation to 90% of the IC saturation will give you the rise time TR. Okay, the addition of delay time and rise time will give you something known as T on. So this T on along with TD and TR is mentioned in transistor datasheet. Okay, transistor datasheet. Okay, which can be regarded as the response time of the switch. Okay, how quickly the switch is able to get into the saturation value is all about the on time. All right. On the other hand, okay, if you pay your attention to ideal switch, okay, at time t equal to t1, all right, at time t equal to t1, when the switch off state is initiated, okay, when you reduce the base current to 0, in case of ideal switch, what happens? The collector current immediately falls to 0. Okay, and immediately the switch gets into cutoff region. Okay, this is the ideal characteristic. Okay, the moment when you reduce base current to 0 at time t equal to t1, the collector current falls to 0 instantly. Okay, now let's look at the practical switching. In case of practical switching, okay, you can clearly observe that at time t equal to t1, Okay, when the base current of the transistor is reduced to zero, okay, the collector current doesn't fall to zero instantly. Instead, the collector current takes a finite time to reach to 0 ampere state. Okay, so that delay basically give you something known as the off time of the device. Okay, now this off time is composed of two parts. Okay, the storage time and the fall time. Okay, now if you look at the bipolar junction transistor structure, you know that the bipolar junction transistor is composed of majority charge carriers as well as minority charge carriers. Okay, now when you initiate the turn-off phenomenon in transistor switch, what happens is that the minority charge carriers, which are present in the opposite layer, okay, needs some small amount of time to return to the original state. Okay, so there will be a small time taken or time borrowed by the minority charge carriers to go back to the majority charge carrier state. Okay, so that time interval is called as the storage time TS. Okay, so the storage time TS refers to the retention time. Okay, so in this retention time, what happens is that the minority charge carriers they move back to their respective majority charge carrier state. Okay, that means to say electrons which are there in p layer tries to go back to the majority state, which is the n layer. Okay, so that is what happens. Okay, once this storage time is elapsed, the collector current falls to zero rather quickly. Okay, however, the time fall or the fall time is measured from the change in collector current from 90% to 10% of IC saturation value. So the fall time is defined as the time taken by the collector current to reduce from 90% of IC saturation value to 10% of IC saturation value. All right, and then the collector current gradually reduces to zero. Okay, so you don't have to wait for this 0 ampere state. Okay, if your collector current has reduced to 10% of IC saturation, it is good enough for calculating the turn-off time. Okay, so the turn-off time is the summation of storage time plus fall time. Okay, so storage time is the time taken by the transistor to push the minority charge carriers to the majority carrier state. Okay, charge carrier state. And fall time is the time taken by the collector current to fall from 90% of IC saturation value to 10% of IC saturation value. Okay, so this transistor, switching characteristics, normally it is asked for 6 marks. Okay, so what you have to do is, you have to draw the practical characteristics. Ideal characteristics you need not draw. Okay, I have drawn ideal characteristics just to compare, the shape of ideal curve with the practical curve. All right, so that's your ideal and practical transistor characteristics. Okay, fine. Now let us come back to something known as the switching operation. Okay, so what kind of circuit you are going to rig up in order to get the transistor switching operation. Okay, so the circuit diagram shown below gives a simple transistor switching circuit. Okay, so basically, this particular circuit, it follows fixed bias network, right? It's a fixed bias network. You can clearly observe that base is connected with RB, collector is connected with RC, and emitter is directly held at ground potential. Okay, so it's a fixed bias network. Now, you look at the type of input which is connected at the base terminal. Okay, so the input which is connected at the base terminal is a pulsed signal, right? A pulsed input. Okay. So Vi over here represents a train of on and off pulses. Okay. So in short, you can call it as a pulsed input. Okay. Pulsed input as in it will have an on pulse and it will have an off pulse, and it's a periodic signal, so one cycle after the other, the shape of the wave repeats itself. All right, fine. Now what we have to do over here is that what happens when an on pulse is coupled to the base terminal, and what happens to the transistor operation when an off pulse is fed to the transistor input terminal. Okay, so let us break down the analysis into two parts. Okay, when Vi is equal to, let's say, Vm, okay, the maximum value of the input. Okay. When Vi is equal to, let's say, V. Okay, all right. Okay, so when your input attains maximum value, we would say on pulse of the input. On pulse of the input. Okay. When Vi is connected to the transistor base terminal, okay, and when Vi attains the maximum value, what happens is that the base current flows. Okay, because there is a voltage, so there will be a flow of base current. Okay, so this base current, okay, will drive the collector current. So when IB flows, IC will also be flowing. Okay, because it's a current control device. All right, now you can apply the simple, you know, Kirchhoff's voltage analysis to find out the magnitude of base current. Okay, so you can just apply, KVL in the clockwise direction. So basically, you can write when you apply KVL, Vi minus IB into RB, okay, minus VBE. I haven't shown, but you understand, right? There will be a terminal voltage between base and emitter terminal, right? So minus VBE is equal to 0. That implies, okay, so that implies your base current IB is equal to difference in potential, that is Vi minus VBE, okay, divided by the resistance RB. Okay, so that's your base current. Okay, fine. Once the base current is known, okay, you can determine the collector current. So collector current going to be beta times IB, okay, or you can also determine the collector current from the output circuit, okay, or IC can be found from the output circuit. Okay, fine. Let's pay our attention to the output circuit. Okay, on the output circuit, you can write the KVL equation as a VCC minus IC into RC minus VCE is equal to 0. Okay, and also note that the output voltage V0, okay, output voltage V0 is what? It is VC, that is voltage measured from collector to ground. Okay, now if you observe closely, between collector and ground, what voltage is coming? Can anyone quickly tell me? Between collector and ground, what voltage is coming on the output side? Can anyone tell me quickly? V0 is VC, right? V0 is VC, and VC is what? VCE.
VCE plus V.
VCE plus VE.
Right. Now, between collector and ground terminal, what voltage you are going to trace out? You're going to trace out collector to emitter voltage, because emitter is already held at ground potential, right? So output voltage is nothing but VCE. Okay, say this is your equation 2. Sorry. Okay. Further, you can modify this equation to get the value of IC. So IC is VCC minus VCE divided by RC. Let me take this as equation 2 and this as equation 3. Okay, where VCE is nothing but the output voltage. Fine. Now, when IB flows, okay, you know that IC flows. IC flows. Okay. Now, in case of transistor switching, okay, okay, RB is selected in such a way that IB is maximum. Okay, so the selection of RB is done, in a manner that your base current becomes maximum. Because if you have IB max, you can expect a very high collector current. Okay, so that high collector current can be considered as IC saturation, because that is what you wanted for on state, right? You want your collector current to be maximum in order to have on state. Okay, so how will you increase the collector current? You can increase the collector current simply by increasing the base current, right? Because transistor BJT is a current control device. Okay, so as per equation 1, okay, you can see that as RB is lessened, or when you start reducing the resistance value, what happens to base current? Base current starts increasing. So unlike your normal biasing network, in case of switching network, the value of RB is smaller, right? A smaller value of RB will give you a higher base current, okay, or a larger base current, and larger base current, okay, will give you a larger collector current. Okay, and thereby you can maintain the transistor in saturation region. So with high IC, transistor is driven into saturation region. Okay, now in saturation region, okay, we have seen that. Okay, quickly let me draw the transistor output characteristics. Okay, so in saturation region, so whenever, let's say this is my final graph, okay, in saturation region, okay, if I were to take out the coordinates of Q point, okay, this is my IC saturation, or sorry, ICQ, and this is going to be my VCEQ. Okay, now in saturation region, your VCEQ point is very close to 0 volts. Okay, so this VCEQ can be approximately written as 0 volts. 0 volts. Therefore, IC, okay, that is equation 2. Okay, go back to equation 2. Equation 2 says IC is equal to VCC minus VC divided by RC. So IC can be written as VCC minus VCE, but VCE is very close to 0. So it is VCC minus 0 divided by RC. And that's the reason this IC can be taken as IC saturation. So IC saturation is VCC by RC. VCC by RC. Okay. So current is maximum. Okay. So when VI is equal to V, IC is IC saturation. Okay. That is maximum current. And V naught, that is the output voltage, which is nothing but VCE, is equal to 0 volts. Okay, so 0 voltage. So maximum current, but 0 voltage. refers to closed switch operation or short circuit operation, closed switch operation. So when there is an input, present at the base terminal, will give you the on operation of the transistor, okay, or the closed switch operation of the transistor, okay. So under this condition, okay, the transistor may be considered as a closed switch. So what happens is that the collector and emitter terminal gets short circuited, okay, due to which a very large current IC saturation flows through the device. So this is the equivalent circuit for closed switch operation. Okay, fine. Now let us look at the dual condition. That is, what happens when you make your input pulse as 0. Okay. Also, you observe that when your input is maximum, output is 0. Okay. So let me go here. So for on pulse, okay, your input is maximum, but your output is 0. Okay, because under short circuit, your output voltage is 0, whereas output current will be maximum. Okay, so this is kind of your NOT gate operation. So NOT gate operation is basically a switching operation. Okay, so inside your NOT gate, you will find such a circuit kept inside. Okay, so NOT gate is made up of this type of transistor circuit. Okay, fine. When you make your input as 0 volt, okay, so when you make Vi is equal to 0, what happens? Base current becomes 0. When base current becomes 0, the collector current also becomes 0. All right, so when collector current becomes 0, what happens to the switching operation? So when collector current becomes 0, okay, you can once again investigate this particular circuit scenario using your transistor output characteristics or the load line. Okay, so collector current is 0. Okay, so you can write the output equation as VCC minus IC into RC minus VCE is equal to 0, the output equation. So collector current is 0, hence you will get VCC is equal to VCE. So this itself can be taken as VCE saturation. So basically your Q point comes to x-axis when you reduce your input voltage to 0. Okay, so Q point. So the value of this Q point going to be VCEQ and the value is VCC. Okay, so at this particular point, your current is 0 amperes, but your voltage is VCE saturation. So current is 0. Okay, voltage is maximum. So this particular circuit phenomenon, refers to open circuit. Open circuit. In case of open circuit, current will be 0 and voltage will be maximum. So when you make your input pulse to 0 volt, your equivalent circuit for the transistor can be given something like this. This is your base, collector, and emitter. So since the current is 0, there will be an open circuit between collector and emitter terminal, and you can say that IC is equal to 0. Okay, so this is the equivalent circuit for open switch operation. Okay, therefore the output voltage V0. Okay, what is output voltage V0? Is VC, and that itself is VCE. Okay, so when you have Vi is equal to 0, let me go up. See, when you have Vi is equal to 0 volt, okay, let's say this is T1 interval and this is also T1 interval. Okay, So when input is 0, your output is VCC. Your output is VCC. So that is what is not get. If you give high input, output will be at low state. And if you give 0 state as the input, the output jumps to high state. Okay, so that is your switching operation. So this switching operation, okay, may be asked for once again 6 to 8 marks. Very, very important switching operation. Okay, and the same analogy will be used in even in power electronics also. All right, the switching transistor operation. Okay, did you understand the switching operation of the transistor? Why it is called as NOT gate operation, and why the current and voltages are going to change their states for high state of the input and low state of the input. Did you understand?
Yes, sir.
Okay,
Yes, sir.
fine. Next, let us come to the design operation. Design operation. Okay. Now, this design operation will help you in achieving proper switching operation. Okay, so design operation helps in achieving, okay, helps in obtaining, okay, proper switching. Proper switching. Now, what do we do in order to get the proper switching operation? Okay, so we use this formula actually. Okay, now in order to get proper switching, what we have to do is we have to set IB, okay, greater than IB max. Okay, we have to set IB greater than IB max. Let me tell you what is IB max. Where IB max is basically IC saturation divided by beta. Okay, so this IC saturation can be obtained from transistor output equation. Transistor output equation. Solve the problems, you'll be able to know. Okay, but before that, I have to introduce you a few terminologies. So you have to set IB greater than IB max. And how do you get IB max value? IB max value is obtained from this particular equation. Okay, fine. Now, normally, as a rule of thumb, as a design rule, okay, take IB is equal to 1.2 to 1.5 times IB max. Are you understanding? As a design rule, okay, you have to take IB as 1.2 to 1.5 times IB maximum. Say, for example, you have obtained IB max as 20 microamperes. Okay. Example I'll write. So your circuit base current, you have to take it as, let's say 1.5 times 20 microamperes. So that is 30 microamperes. Okay. This is what I wanted to, convey. Okay. That is 120 to 150% of IB max you are supposed to take. Okay, normally, I take the upper limit because greater the value of base current, greater will be the collector current, and better will be the saturation state of the transistor. Okay. Okay. Once this IB is found, okay, you can find RB, the base resistance. So RB is VCC. RB is VI minus VBE. Divided by IB. Okay, so IB is substituted from the previous step. So 3-step approach you have to follow. First step, find IB max. Second step, set IB by taking IB max by multiplying IB max with 1.2 to 1.5. Okay, so 1.2 to 1.5 going to be the multiplication factor, and in the third step you can design the base resistor. Okay, this is what we use it for our design problems. Okay, fine. Okay, now let us solve one design problem. Okay, take down for the transistor inverter shown below. For the transistor inverter shown below, determine for the transistor inverter shown below, determine RB and RC. Okay, so you need to design the values of RB and RC. So it's a design problem. Okay, take IC saturation is equal to 12 milliamperes. Okay, and HFE is equal to 200. HFE is equal to 200. The input signal is given something like this. $10 volt, this is 0 volt. This is your input signal. Okay, and the output signal is given something like this. This is your output wave. Okay. Sorry, this is 12 volt. Beg your pardon, this is 12 volts. So output is given something like this. So this is 12 volt and this is 0 volt. Okay, input and output. So you need to design the transistor switching. Okay. Okay, I hope you understood the question. For the given set of specification, you need to find the values of RB and RC. So input signal status is given, output signal status is given, along with the saturation current of transistor is given, and HFE is given. Okay, so this HFE is nothing but beta. Okay, this is called as H parameter. Okay, in module 2, I'm going to tell you. And this is called as RE parameter. Okay, there are two models for transistor, RE model and H model. Okay, each model will take different convention. So beta and HFE are the same. Okay, so that's 200. Okay, fine. Since it's a design problem, so first of all we need to draw the circuit. Okay, that's how you have to do it in your externals as well. First you draw the circuit. So this is your RB. Okay, the emitter is directly held at ground potential, and the collector terminal is connected to collector resistor RC, and this is your VCC. And what is VCC? VCC is actually 12 volt. Whether they give or not, always remember that output voltage, okay, is VC and VC is VCC. Okay. So that's your VCC, 12 volt. Okay, this is where you connect your pulsed input. Okay, so this is your IB, IC, IA. Okay, all right. So given IC saturation, right, is equal to 12 milliamperes. Hence you can find, so IC saturation is what? Basically maximum collector current. So maximum collector current is given, hence you can find IB max, the maximum base current, which is IC saturation divided by beta. So 12 milliamperes divided by beta, beta is 200. Okay, how much it gives? $60 micro. So IB max is 60 micro. Okay. Once IB max is known, Okay, what you can do is set IB value, okay, from the design rule. So let us take IB is equal to 1.5 times IB max. Okay, so our base current going to be 1.5 times the maximum base current, which was found in the previous step. So that is 60 micro. So that is 90 micro amperes. So what you are trying to do is you are trying to circulate 90 microamperes of current through the base terminal by appropriately selecting RB value. Okay, so we can find RB value. So therefore, resistance RB is equal to difference in potential VI minus VBE divided by IB. Okay, so what is, okay, and here let me write, when VI is equal to V is equal to 12 volts, IB flows. Okay, so this VI should be assigned with the 12 volt value. When VI is equal to 12 volt, the collector current, sorry, the base current flows, right? So when VI is equal to 12, your base to emitter voltage is 0.7 for silicon transistor and 90 microamperes in the denominator. So you will get RB as 12 minus 0.7 divided by 90. Okay, you will get it as, how much you'll get? Approximately 125.55 kilo ohm. So that's your base resistance value. So that means to say, if you connect a resistance of 125.55 kilo ohm, you will be able to maintain a very good base current that will help you in achieving proper transistor switching operation. All right. So RB is determined 125.55 kilo ohm. Let's substitute in the circuit diagram. 125.55 kilo ohm. Done. Next, let us go for RC. Okay. So to find RC, you can go for the output equation. Output equation. Okay. So once again, when VI is equal to V is equal to 12 volts, you can write VCC minus ICRC minus VCE is equal to 0. Okay. So under on state, VCE is approximately 0 volts. We have seen because your VCE lies very close to the origin. Okay, for on state operation. Hence, you can write RC is equal to VCC divided by IC. Okay, that is VCC divided by IC saturation. Okay, and IC is equal to IC saturation, right? For on operation of the device. So that's 12 divided by 12 milli. So that gives you 1 kilo ohm resistance value. So your RC value going to be 1 kilo ohm. Okay. So that concludes your design problem. That concludes your design problem. Is it okay? Did you understand?
Yes, sir.
Since there is some time left, what I will do, quickly I will solve a problem from stability. Okay. Transistor stability. Okay. One problem I will solve and one I will give for quiz. Okay. So you will be able to, solve if you know this particular problem. All right. Fine. The question goes like this. Determine the stability factor. Okay, let me just write. Determine the stability factor. Yes, VBE and change in IC. Yes, VBE and change in IC from 25 degrees Celsius to 100 degrees Celsius. Okay, 100 degrees Celsius. For the transistor with VBE at 25 degrees Celsius is equal to 0.65 volts, and VBE at 100 degrees Celsius is equal to 0.48 volts. Okay, all right. So there are two temperatures, 25 degrees Celsius and 100 degrees Celsius. You know that VBE depends on the temperature value. Okay, as the temperature starts increasing, VBE starts reducing. So at 25 degrees Celsius, probably the room temperature, it is at 0.65 volts level. And when the VBE is increased to 100 degrees Celsius, the voltage has dropped to 0.48 volts. Okay, for the following biasing arrangement. So SVBE and change in IC for this particular circuit condition, you need to do it for the following arrangements. Fixed bias, FB fixed bias, with RB is equal to 270 kilo ohm and beta is equal to 120. Second, emitter bias. Okay, I'll use the short form. EB means emitter bias, with RB is equal to 39 kilo ohm, RE is equal to 1.2 kilo ohm, and beta is equal to 120. Okay. Third one, voltage divider bias, with R1 is equal to 39 kilo, R2 is equal to 10 kilo. This is 39 kilo ohm, okay, not 3.9 kilo ohm, what you did in exam. This is RE is equal to 1 kilo ohm and beta is equal to 120. Okay, all right. So this is the problem. So you need to find out SVB. So let's write down the objective. Okay, objective of this problem is to find SVB and delta IC for the three circuits: emitter bias, fixed bias, and voltage divider bias for T1 is equal to 25 degree and T2 is equal to 100 degrees Celsius. So when the temperature is changing from 25 to 100 degrees Celsius, what happens to SVB and delta IC value? All right. All right. So first, let us find out delta VBE, change in base emitter voltage. So delta VBE is equal to VBE, okay, at a later temperature minus VBE at the initial temperature. Okay, and that is 0.48 minus 0.65. Okay, it gives minus 0.17 volts. So we have found delta VBE. All right. Now let us go to the fixed bias circuit. Fixed bias circuit. Now, in case of fixed bias circuit, we have found that SVB is equal to minus beta divided by RP. Minus beta divided by RP. Okay, this you have to solve it. Okay, you have to find it. We have done it for voltage divider bias. So similarly, you could do it for fixed bias circuit. So SVB for a fixed bias circuit is minus beta divided by RP. So that is minus 120, because beta is given as 120. Okay, divided by RB. Okay, what is RB? 270 kilo. Okay. So that gives the value as minus 0.44 into 10 to the power minus 3. Okay. Fine. Now, how do you find? So SVB you have found. Okay, how do you find delta IC? Okay, remember one thing. What is the definition of SVB? So SVB is defined as change in collector current due to the changes in um, base emitter voltage. Okay, so that implies your delta IC or change in collector current IC can be found simply by multiplying the stability factor with change in VBE. Okay, so this is the formula which we use to determine the delta IC. Okay, so what is it? SVB, we have already found. Minus 0.44 into 10 to the power minus 3 into delta VBE. Delta VBE was, I mean, we found the value, right? We have already found. So it is negative 0.17. So, sorry. So when you multiply the two negative numbers, you will get delta IC is equal to 74.8 microamperes. All right, so that is for fixed bias. Once fixed bias is done, you can go for voltage, emitter bias. Let's go in sequence. Emitter bias. Now, in case of emitter bias, okay, SVB is minus beta divided by RB plus 1 plus beta times RE. You see, you don't have to by heart. In fixed bias, there is no emitter resistor, hence there is no RE. In emitter bias, there is emitter resistor, hence, you will have the reflection of emitter resistor in the input side. So that's the reason 1 plus beta has come into picture. Okay, so that is equal to minus 120 divided by RB. So for emitter bias, RB is 39 kilo ohm. Okay, so it is 39K plus 121, because 1 plus 120 is 121 into RE. RE is 1.2 kilo ohm. Okay, so I have already calculated the value. So yes, VB, you will get it as minus 0.65 into 10 to the power minus 3. Okay, so having known SVB will enable you to find the stability, the change in collector current IC, that is SVBE into delta VBE as discussed in the previous case. So minus 0.65 milli into minus 0.17. So delta IC, you will get it as 110 microamperes. 110 microamperes. Okay, so that's the change in collector current. And finally, you can do it for voltage divider bias. Okay, if you know emitter bias formula, you can write it for voltage divider bias circuit. Okay, so yes, VBE for a voltage divider bias circuit is minus beta divided by, in place of RB, you have RTH, the Thevenin's resistance. Okay, and then rest all remains the same. RE, okay, where RTH is R1 parallel with R2. So that's 39 kilo ohm parallel with 10 kilo ohm. Okay, so that you will get it as 7.95 kilo ohm. Okay, please check my calculations. Okay, so your SVB becomes minus 120 divided by 7.95 kilo plus 121 times 1 kilo. So yes, VBE will be minus 0.93 milli. Okay, that's okay. Or I would write 10 to the power minus 3. Okay, so therefore, delta IC is SVBE into delta VBE. Okay, and that is equal to minus 0.93 milli into minus 0.17 volts. So delta IC, you will get it as 158.1 microamperes. Okay, so that's your delta IC. Okay, So this is how you solve the stability problems. Okay, very simple, formula driven. Okay, only thing is that you must solve or practice the stability expressions. Okay, fine. So that's all. So that's the end of module 1. Okay, and tomorrow let me start with module 2. Okay, it won't take much time to complete module 2. Okay, because already the concepts being discussed in module 1. Okay, fine then. Do you have any doubts? Do you have any doubts?
No, sir, it's clear.
It's clear. Okay, all right then. Fine. You can join the 4th hour class then. All right. I'll stop the recording. Today I will send you a quiz. Okay, please try to answer that.